Hi everyone, today I'm covering a topic that interconnects to a whole bunch of things I've been doing on my channel. The reason why I want to cover it in this video is because I'm starting to work with language models. I recently made a video that shows you how to load a language model called small-lm. This model is compatible with JavaScript and runs locally right in the browser. And we can do things like prompt the model. Let's say I were to prompt the model with just one word. So usually if you're working with a language model, you're probably prompting it with a sentence, a paragraph, a lot of stuff. But just to simplify things, imagine if you're asking it to fill in a blank. Hello, blank. What might come out? Well, maybe what might come out is the word world. Maybe what might come out is the word how. Maybe the model somehow knows who I am. Maybe it's going to say Dan. And if you've ever worked with a language model before, you might notice that even with the same prompt, you don't get the exact same output every single time. That's because, yes, the language model, what it's doing is predicting the next token, or an oversimplified way of thinking of it is the next word. It's selecting from a table of probabilities. Maybe world is 80%, how is 15%, Dan is 5%. That's what the neural network architecture is doing. It's encoding the input text, and maybe I'll come back and do a deeper dive into some of these pieces in another video, processing it through the neural network, and the output of the neural network is a giant table of all the possible next tokens in its vocabulary, along with probabilities. So this begs the question, how are these probabilities calculated? And then why would you sometimes want to adjust these probabilities? Maybe you want to flatten the probability so that the lower probability words like Dan actually have a higher chance of being picked and the higher probability ones have a lower. Or maybe you want to stretch the probability so that world is even more likely than 80%. So these are the things I want to explain in this video. Softmax being the mathematical operation that takes the output of a neural network and turns it into probabilities. And temperature being a property that can be applied mathematically to those probabilities to adjust them in one direction or the other. However, it's important to note that these concepts of softmax and temperature are not the exclusive domain of large language models. And that's where I want to travel back in time to many, many years ago, an old coding challenge on the coding train, Markov chains. Because I need a new name, and what I'm going to do is I'm going to generate one using an algorithm called the Markov chain. I'm not going to rehash the entire Markov chain coding challenge, but let me give you a quick high-level overview of what's happening in it and talk about what I'm going to change to add the concepts of softmax and temperature to it. This wonderful post by Victor Powell, I think, does the best job explaining the core concept of a Markov chain. We have a system that has a number of possible states, maybe just two states, A and B, and it hops from one state to another based on probabilities. So in this case, A has a 50% chance of staying at A or switching to B, and B is the same. Now I've changed the probability to be 90% likely to stay in A, and you can see how the behavior of the system changes. Markov chains can be used to study financial systems, weather systems, all sorts of systems where there's sequential data or sequential events, and you want to investigate predicting the future or analyzing the sequence based on historical data. A Markov chain can also be a language model. I could actually replace LLM here with Markov model. Why? Because we can think of the input text to a Markov model as the current state. I have the word hello. That's the state of my system. The Markov model could then be holding a table of the entire vocabulary with probabilities for every word that might follow the word hello. This is one of the things I love about Markov models. If I have a Markov model generating text for me and I'm wondering why is it saying what it's saying? I can open the Markov model and look at the giant table of probabilities. This is very different than a large language model that is a neural network-based system that's just estimating probabilities. It's been trained with massive amounts of data, and by the time you're using it, that data is so far away you can't make those connections anymore. This is a wonderful visualization of this idea by Chris Harrison. It's using text from a 2006 Google dataset and visualizing the frequency of words that come after the word I, for example. have being most likely, m second, etc., and then further words after that. So this is my Markov chain example, which I think was made so long ago. It was before I even called this channel the coding train. So I think it's trying to name the channel. Let's see what we get. Code red coding flock go. The sky. The code kitchenamo. I'm rebranding the channel, everybody. The code kitchenamo. I should also mention that a Markov model for text, a Markov chain, doesn't typically consider just one word as the state. It usually looks at 2 words or 3 words or 4 words and tries to use that to predict what would be the next word. And in fact, in my example, I didn't even use words at all. This is a character level Markov chain, meaning it's looking at just sequences of 3 characters or 4 characters in a row and then creating a table of probabilities of what character would be next. Sequences of 3 words or 4 characters, those are known as n-grams, and the term order is usually applied to what is the value of n. Are we looking at collections of 3, of 4? That's the order. So in this code, you can see there's a variable called order, and then there's this object called n-grams. This example is loading this text file, which has all sorts of made-up names for what could be a name of a YouTube channel about coding, I guess. Then, if we look at the n-grams object in the console, notice the order is 3. I have every single sequence of 3 characters, including spaces, all listed here. And for every one, like G space C, I have an array of all of the letters that come after it. So look at this. O appears 5 times. So why do I store O 5 times? Well, let's look at space CO. That has D, D, M, D, D. The D is there because there's so many instances of the word code or coding. M, because the M is there from coding comrades. And there's even an L from coding colors. The Markov chain then generates text by looking at what the current state is and then sampling from all of the options of what could come next. What my code does, if the state is space CO, it picks from this big array randomly. So D is more likely to be picked because it's in the array many more times. This is a very crude and simplistic methodology that doesn't allow for the concept of softmax and temperature to be able to adjust the behavior of the Markov chain itself. Hopefully, again, that's the TLDR of what the coding challenge was. I go and build this whole thing if you want to go watch that actual video. At the end of this video, I'm going to come back and update my Markov chain code to use softmax and temperature. But let's first just create a kind of dummy scenario where we can work out the math for these 2 algorithms. I've most likely alluded to or talked about the softmax function in my image classification videos. I have several of those about working with ML5 and TensorFlow.js, as well as the teachable machine system. An image classifier will output a list of labels and probability scores for those labels. But what a neural network actually outputs is not those probability scores. The output of the neural network is often referred to as the raw logits. This is a post about teachable machine, which I've covered extensively on my channel. And in this post, if this image of a cat is passed into the image classifier, you get this giant spike in this visualization of all the probabilities all around different categories of cat. But the raw output of the neural network looks like this. This is the cat logits, the unnormalized score, some value between 10 and -10 across all 1,000 labels that are part of this classification system. So how does it work to go from logits to probabilities? So I have a kind of crude P5.js sketch with simulated output of a neural network. I have an array of labels that each has a name and a score. One thing that I could do, let's just change this turtle score to 0.023. I'm going to write a quick algorithm to normalize all those scores. I can add up all the scores into a sum, take every score, divide it by that sum, and I have normalized probabilities. 67%, 26%, and about 6%. So this is one way just to take any arbitrary scores and normalize them. It's not softmax. And why is this not good enough? Well, one is neural networks will output negative numbers. So if I were to run this code again with a negative score, I get nonsense now in the probabilities. It doesn't work. The other reason for softmax, which we'll get to the math in a second, but I'm just looking at the definition here from Wikipedia, it is an exponential function. So it's allowing for more possibilities of how you might adjust the relative scale of those probabilities. And you can see here, everything that I've said in this very, very long video is summarized in this one sentence. The softmax function is often used as the last activation function of a neural network to normalize the output to a probability distribution over predicted output classes. Let's now put the math into our code. All right, here it is. Yikes! Let's put this on the whiteboard and explain it. All right, let me write out the softmax formula here. Now, on the Wikipedia page, the notation looks a little different. It's using a Greek letter for softmax. But what I'm trying to show you here is softmax of any z equals, and what's z? Z is the array of raw score values, the logits that are coming out of a neural network. So z is an array with 1, 2, 3 values. If we start with index 0, so I is 0, we've got the value 2.3. And I realize I'm saying the standard, I guess, way of notating it here would be from 1 to k, 1 to 3. But in coding, we use counting from 0. So hopefully that's not going to be too confusing here. Let me keep going. So the softmax of 2.3 equals e, and let me say what e is in a minute. Just hold that thought. E to the 2.3 power divided by, okay, what does this mean? This is capital sigma, the Greek letter for summation. So we're going to sum from j equals 1 all the way through k, being there's k possibilities here, every single z value. So also e to the 2.3 plus e to the 0.9 plus e to the negative third power. And we're going to do this for every single one of these. So this is not that different than the standard normalization. You take the value and divide it by the sum of all the values. The difference is each value is the exponent to the equation e to that value. Okay, let's point out a couple things. What is e? E is Euler's number. It's around 2.718, and it is like pi, an irrational number where the digits never repeat with any kind of pattern. This number is the base for the natural logarithm, so it's kind of like a standard in mathematics. There's lots more to say about it. I'll include some more references to Euler's number in the video's description. The point is more that we need to use these values as the exponent. That has this wonderful quality of allowing for two things. One is negative numbers. E to the negative third power is the same as 1 over e to the third power. So with a negative number, we're getting a much, 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 much smaller value. So everything becomes a positive number, but this value is really, really tiny, and it works well for probabilities. The other thing is because these are exponential functions, the higher the score, the greater the probability is. And this is something that we're going to get to tune based on changing what the base of this exponential function is. Quick clarification. Yes, the softmax function is set up in a way that will allow us to tune those probabilities, but we won't be changing the base of the equation. It will always be e. Instead, we'll be taking the exponent, z, and dividing by a value called temperature. And you'll see that momentarily as I go to apply this math. And guess what? Look at this. Right there in P5, we've got the exp function. Calculates the value of Euler's number raised to the power of a number. Perfect. So if I go back to my code, we already actually had the code for adding up all of the scores and dividing by the sum. All we need to do is add up all the scores as the exponent of e to the power of, and that's the new sum, and then add the exp function here as well. And now, even with the turtle having a score of -3, it's got a very, very low 0.3% or 0.4% probability. 20% about for dog and 80% about for cat. All right, now I think to really demonstrate how this works, it would be important for us to have sampling added to this sketch, meaning pick one of the labels based on those probability scores, as well as some kind of visualization to show the frequency of how often those are being picked over time. I'm already trying to do too many things in this one video, I think, kind of half explaining Markov chains and language models and then the softmax function and look at image classification, but hopefully this is interesting to you and you're following me somehow. Good news is I've already made an entire video about weighted selection, the sampling process, and I have covered this extensively in the Nature of Code book in both the chapter on randomness as well as my chapter on evolutionary computing, where we're picking parents in an evolutionary system based on their fitness scores. So I can actually take this weighted selection code and bring it into my sketch. But I can't help myself. Let me give you a very short overview of how this algorithm works before I adapt it into our code. Let's say we have the 3 labels and their probabilities. Our assumption here is these were all calculated via the softmax function. What if I visualized these probabilities in a rectangle? So you can see here, I've drawn this rectangle with each section being scaled according to the probability value. Now imagine if I were to pick a value between 0 and 1. If I pick, 0.7, I'm going to get a cat. So 80% of the time, I'm going to pick a value that's within here, 15% of the time here, and 5% of the time here. That's essentially how my weighted selection function works. Right here, you can see I'm picking a starting point. Now, this is a little bit funny, but as long as start is greater than 0, subtract the fitness. Now, first of all, the fitness here, I'm going to change my code in a second. Actually, let me just rewrite this code to use the score values of this particular sketch. These are called labels. I'm not actually using the score. I'm using the probability. And I'm going to say return labels index.name. Okay, once again, what's happening here? I pick a random number between 0 and 1. As long as that value is greater than 0, I'm going to keep going. And I start subtracting out the probability values and moving through that array. How many of those do I need to go through before I get below 0? Well, you can see if I picked 0.7 and I subtract 0.8, I'm already below 0, so pick the cat. By the way, the order of this doesn't matter. If I pick 0.7 and subtract 0.15, I'm still above 0. And then I subtract 0.05, I'm still above 0. If I were to pick 0.9 and subtract 0.8, I'd still be above 0. I'm at 0.1 and I go to subtract 0.15, now I'm below 0, so pick dog. So I'm only going to get dog if this is the order, if I pick values greater than 0.8, and it would have to be greater than 0.95 for me to get turtle. So this should be a function that every time I run it, picks a random value from my labels array according to the probabilities. Let's add a draw function. Let's run this sketch and see what gets picked. Sorry, there's no I. The variable name in this function is index. So you can see, this isn't the best visualization, but you can see that cat is getting picked quite a bit more often than dog, and turtle comes up very, very rarely. Let's visualize this in a graph. Let's give every label a count. And let's actually not return the name. I don't care about that. Let's just return the index. Then let's draw a graph with growing bars every time it's picked. So the width of each bar is sized according to the width of the canvas. So the height of each bar is the number of times it was picked, count. So the y position, because I want it to grow from the bottom, is height minus h with height. And we'll give these a stroke of 0 and a fill of 127 and draw a white background. And I don't know what I was doing here, but I need to increase the count of the index that I pick every time. Great, we can see how turtle has never been picked. Or maybe it's been picked a couple times. But we could give turtle a higher score just to be sure this is working. And now we can see the probabilities have adjusted accordingly. Great, we're almost done, people. So this is where temperature comes in. One of the things that's wonderful about softmax and is going to allow for temperature, this concept of temperature, is the fact that the raw scores, the logits, if you will, are used as the exponent. So one, we established that's great for having negative scores, but also because this is exponential, a higher score will lead to even higher probability. But what if we want that to be increased even more or turned down a bit? Well, all we would need to do is take this exponent, the exponent, very hard to say, and divide it by temperature. So a temperature of 1 will do absolutely nothing. And by the way, we're going to do it here as well, of course. So the temperature of 1 does nothing. A temperature of 2 has the result of making this exponential power less. So it's squashing those probabilities. They're going to get closer to each other. That's a hot temperature. We're turning up the temperature. If the probabilities are getting less, closer to each other, we're more likely to pick the weird and strange outliers. If the temperature is down, if you think of it's less than 1, 0.5, 0.1, obviously it can't be 0. You can't divide by 0. Then we are increasing that exponential power. And the cat is going to be even more likely to be picked. Let's look at how we add this mathematical property into our code and what it does to the end result. So let me introduce a temperature of 1. Let me go and put turtle back to -3. And let's use a shorter variable named temp for temperature. There you go. A temperature of 1, we have the same result of frequencies that we started with. Temperature of 2. Aha. Look how dog is being picked more. That's the second one from left to right. And turtle's got a whole little bar there. Temperature of 5. Temperature of 1,000. At this point, I've squashed the probabilities so much. It's basically even probability. It's uniform probability distribution. Let's go back to a temperature below 1. 0.5. Yeah, looks like the dog is even less frequent, 0.1. There we go. We can see we're not even getting dog or turtle at all. Okay, that's softmax and temperature. Now, before I leave you, I want to go backwards and apply these concepts to both the Markov chain and a language model. Okay, I'm going to do this quickly. It's a little out of scope for this video, but I'm going to update the Markov chain code to count the frequency of characters, not just add them to an array of options, which is what's happening right here. So we need to check. The next character is that next character. If n-grams, that gram has never seen that next character before, then it should have a count of 1. Otherwise, we should increase its count. So this is me calculating scores for the next character, the frequency of next characters in my Markov model. Let's look at the Markov model again. No, I missed something. Oh, if I had never seen that n-gram before, I made it an array. It needs to actually be an object. They're all not a number. What did I get wrong? Oh, if it hasn't seen it before, it gets a 1. Otherwise, it counts. There we go. Space CO, whenever that group of 3 characters appears, a D follows 19 times, an M once, an L once, and an S once. So now that I've built this model, these need to be converted into probability scores with softmax. And I just want to point out that I'm applying the softmax function to the Markov chain example really just for demonstration purposes. In reality, simply summing all the counts and dividing by that sum is a much better way to do the probabilities here. Adding an exponential function is going to skew them in a really extreme way. Regardless, you can still apply temperature, whether you use softmax or the simple summation, and I'll be showing you that later in this video. Okay, not the most elegant code, but now I have applied the softmax algorithm here. I am looking at every n-gram and all of the characters, taking all those character counts and setting it as the exponent, e to the character count, summing that up, and then dividing e to the character count divided by that sum. And now you can see I've set the values to those probabilities. D has a 99.999% chance, MLS a much lower probability. Now I need to grab this weighted selection function and bring it into the Markov chain. I think it would make much more sense for this function to receive an array as its argument. I'm going to assume that array, I called it options, but maybe it's probabilities. It's an array of probabilities, and it gives back the index, picking based on the raw value of the probabilities. Now here is the sampling. Before, possibilities was just an array of all the characters with many characters multiple times. Now I need to sample based off the weighted selection function, which is assuming an array of probabilities. So I'm going to say probs for probabilities is the values of the possibilities. The possibilities object is now key value pairs, character probability, character probability. So I can get an array of all the probabilities with object.values, and an array of all the characters with object.keys. So we sample from the probabilities, and the next character, the next index, that's what getting back is the character's next index. So this is the new sampling based off of that array of probabilities. And of course, there's other ways to organize the code and think about it, but this is just the way I'm doing it now. Ooh, undefined. What did I miss here? Whoops, the whole point is I'm no longer using a random one. Weighted selection. That's going to give me the index. There we go. And finally, we can now add temperature. Let's start with a temperature of 2 just to see something that feels maybe a little different. And again, let me call it temp for short. And here, remember, all we're doing is we're taking the raw scores and dividing by temperature. Hapeering Unicoding Me, the new name for this channel. Now, let's take a look at this in the context of a large language model. I've loaded in this model, small version 2, 1.7 billion parameters from Hugging Face. You can see my other video where I go through how to use Transformers.js and load this model into a P5.js sketch. I've got the classic prompt that everyone loves to ask their favorite large language model. How many R's in strawberry? Strawberries have 1 R in their spelling, which is definitely correct. Now, what's going to happen if I press submit multiple times? I am getting the same exact response every single time. This is because the Transformers.js library with the text generation task, when you ask it to generate, by default, it actually doesn't do any sampling. It just looks for the single next token with the highest probability. This is what's known as argmax. Don't bother to sample, just find the one with the highest value, pick that one every time. It's essentially equivalent to having a temperature of 0, by the way. You've stretched the probabilities so far that the highest one is 100% and everything is at 0. If I want the library to perform sampling, I need to add this property to my generate function. By the way, I called this pipe because I am getting the text generation pipeline, but I actually think it would be nicer to name this variable what it does, which we could call it like a generator. So now I'm awaiting generating the text, a maximum number of tokens, 128, based on these messages that have gone in. You can see I've commented out the system prompt and I was doing some experiments with that, which you're also might like to play with. Now I'm going to add do sample true. So now it will perform weighted sampling. Now you can see I'm getting wildly different responses each time. Let's lower the temperature. This is a little too hot for me. I can add another property, temperature. Let's give it a fairly low temperature, 0.1. So you can see I'm still getting some variation, but notice there's a more repeating pattern. There's maybe less variety here. I'm not getting the correct answer. That's a whole nother discussion that we could have about this particular model and this kind of query. But let's just turn the temperature way up. Let's make it pretty hot. Let's set it to 5. Now I'm just getting total nonsense because the actual probabilities that this neural network-based system is calculating based off its training data is almost gone. It's just giving me random stuff. Let's just throw in a slider so that we can adjust this in real time. In P5, you can make a slider with, I think you give it the initial value, then the range. Actually, I'm forgetting. I think it's the range, 0.1 to 2. Let's give an initial value of 1 and a step of 0.01. Actually, let's let the temperature go up to 4. Let's turn the slider down. We can see I'm getting this sort of like classic pattern with less variation. Turn the slider all the way up. And I'm getting something completely unrelated to my query, all about here berries, which sounds delicious. Since this video is already 100 years long, I should probably mention a couple other things. So we talked about softmax. We talked about temperature. Softmax being the mathematical function to calculate all of the probabilities based off of raw scores. Temperature being a way to squash or stretch those probabilities. But you'll also see terms like top K as well as top P. And these are kind of variations off of temperature. Not really variations, but they're also properties that allow you to adjust the way the sampling happens. Top K is actually the same thing in a way as argmax. So argmax is top K with a K of 1. But what top K does, if I had a K of 3 and I had 1,000 possibilities, I'm only going to pick from the top 3. So it's a way of allowing sampling to still happen, but reduce the number of possibilities to only the most common ones. So that's a property you could adjust also in the generate function, as well as top P, which is like top K, but instead of only picking the top N number, or top K, of options, you're picking only the options within a certain probability threshold. So for example, a top P of 50% would use, well, in this case, it would only use world because it's already above 50%. But you could imagine taking all of the most frequent options and adding them all up. And as soon as you got above 50%, you stop and let all the other ones go to the wayside. Generally speaking, I'm just using temperature if I'm playing around with this stuff and trying to make creative applications with it. You might get confused if you start using top P along with temperature, though you absolutely could. But these are some different properties you could use to adjust the way the sampling behaves. If you made it all the way to the end of this video, congratulations, gold star for you. I don't know where this is gonna live on the Coding Train website, maybe in a playlist about Transformers.js and machine learning or somewhere else. But if it's there, I would love for you to submit anything that you make based off of watching this video. For example, you could make a much more dynamic and interesting visualization of taking a raw set of scores and applying weighted selection and adjusting with temperature. Here's a version that I'll share with you that just has a slider and a bit of fancier visualization, but you could probably be much more creative than this, and I'd love to see that. I also have a nicer, more cleaned up version of the Markov chain example with weighted selection and temperature. And here you can see that I'm not actually applying softmax to the raw counts. I can just use those raw counts themselves, and to apply temperature, set them to the power of 1 divided by temperature. And this will have the same desired result. A lower temperature will widen those probabilities, and a higher temperature will flatten them. Maybe there's some type of creative visualization you could do to show how the Markov chain is building and picking new text, or you could load your own data into it in some creative way that I'd love to see. And then of course, I'm sure there's so many creative and interesting improvements you could do off of this base Transformers.js language model with temperature example that I've made. So please let me know in the comments, did this video teach you something meaningful? I don't know anymore. And I hope you enjoyed it, and share with me what you make, and I'll see you next time on the Coding Train.